This network. Is it too full? The network went down. Sorry for that.
Oh, okay. It's fine.
Wait. Okay, so I was saying. Okay, so we were at the incline object. So we were saying if this is your surface, okay, then you place an object on this surface. Now trying to see how do I rotate this. Let's see. Okay, but let's just do it better way. Okay, let's say if this is the edge here. Can't find where do I rotate this object. Okay, so if this is the object, and let's suppose this is the edge supposed to touch nicely. Or can I be able to draw nice better? Because this. Let me say if that is your. Draw now. I want to clear this.
Hurry up and bring some water for my grandson. Grandma, please stop Ganga. She can't leave. Oh, my sweet grandson. Look, yesterday you agreed, so what happened now? Remember yesterday you said to me that you...
Okay, so if this is your surface, the one that I'm drawing here. Okay, that is your surface. And then you place an object. Okay, and this one you can see that the surface is placed with an angle. Okay, so you can see that your surface makes up an angle. So, and we said that the normal force is always perpendicular to the surface. If this is the surface, then now it's no more going up on this case. It's no more going up like this, like what we were doing on the horizontal. Okay, so if we consider this is our horizontal surface, then our normal force is now going up on this direction.
Of course.
But our weight is not going on this direction. The surface here, our weight is going up in
They are so selfish, all they care about is themselves.
it is our weight.
Okay,
so we'll see that this perpendicular, the normal force, which is now that you can see that your weight is acting in components. Your weight has a component acting in the component in the x direction. In this direction, and we have a weight which is acting on that direction. So now here your weight or your normal force, it's perpendicular to what? So then your normal force is now opposing which force? Is opposing the force when it is inclined. Your normal force is opposing which force? The force that are acting in vertical is the force of. So in vertical we only have the normal force and the weight in y. So if we do some the forces that are acting in the y direction, vertical component, then we take this is our y and this is our x. So this is our positive y and this is our positive x. Let's say this object is not moving. Okay, if this object is in the equilibrium, then we have that a weight, a normal force, then have a normal force which is acting upward, which is the positive, minus a weight, but this weight is the one which is acting in what? In y components, and this object is not moving, there is no acceleration in the y component, so we say that is equals to 0. So if there is no acceleration in so therefore in this case your normal force is equals to the weight which is acting in what? Acting in y components. That is why we say, so if we look up on this case, we see that a normal force is not equals to the weight. It is not always true like a normal force equals to the weight. It's only true if a normal force is placed on the horizontal and you have an object and there's a weight acting there, and this is a normal force. Then in this case, no other forces are acting on the object, then we have that a normal force is equals to the weight. Okay. So we see the three cases. We've seen the three cases. Now we just wanna do a bit of an example. Okay, if a box is sitting on the table, experience a normal force N. Okay, so if you push down the box, okay, if you push down on the box, what will happen to the normal force? Will it increase? Will it decrease? Or will it stay the same? Okay, so if we look, okay, so if we have that question, it's placed, we have a box, a box which is placed on the horizontal surface. So on this box, automatically the moment the box is there, we have a weight, we have a normal force. Now if you push this box down, you push this box down with force. Okay, so we can take our positive y to be on the upward. Now if you push this box downward with that force, what will happen to the normal force? Okay, so we see that if I do Newton's second law that says the summation of the forces is equals to the mass times what? Times the acceleration. So what are the forces acting? So we have a normal force minus the weight minus the applied force. This is equals to 0. Okay, the box is not moving. So then we have that a normal force is equals to the weight plus force. Okay, so remember that it's a sitting, a box is sitting, it means it's not moving. That's why there we had equals to 0. So what will happen if the box increase? I mean the normal is decreased. In order for that box still to be kept not moving, what happens to that to the normal force. So if you look up on that case, the case 2 that we had here, you apply a force. This is almost now the same question that comes now. You apply a force downwards because you are pushing this box downwards. Then in order for this box to remain at rest, not moving at all, what should happen to the normal force? So and this is just what we were doing. A normal force, it's going to be equals to, we said if it's not moving, then we sum up all the forces, then we get that a normal force is equal to the weight plus force. So it means you increase the weight. I mean, a normal force. It's the summation of your forces. Okay, question 2. A box of MSM sits on an inclined plane. What is the relationship between the weight of the box and the magnitude of the normal force exerted on the object? Okay, so if you just look up also in that case,
From today onwards, don't talk to me.
then you will see that this, because if you look up at the same, this is just the same as what we were doing up there. Okay, so what is the relationship between the what? The weight and the magnitude of the normal force. Okay, so we have that a normal force, it's drawn perpendicular to the surface, and that is your weight. So we have that the magnitude of the weight is greater than the magnitude of the normal force exerted on the object. Why? Because we look up on the same, if we look up the same one that we had here when we were doing the incline, we say if this is an object, I mean this is the surface, and this is the weight. I mean this is the object. Okay, so the weight is pointing towards the gravitational toward the earth, the center of the earth. Then here the perpendicular surface of this one is on the, just the drawing, but I hope you understand. Okay, it's in that direction. So you can see that the weight is acting on that direction. So this is the weight on the x, and we have a weight which is now perpendicular to that surface. So let me just say if you see this thing drawn up with an angle, let me say, so we can maybe understand better. Let's say if theta is equals to 30. Do you have a calculator?
Yes.
Okay. So and let's say the mass is equals to 20. If that object has a 20. Okay, so if we calculate this, we say if there is no motion, we said previously that the normal force, the forces acting in y is equal to the normal force minus the weight in y. It's going to be equals to 0. Okay, so we have that a normal force is equals to the weight in y. So what is the weight in y? We said if we apply that, this is with the horizontal surface. So if we apply that, then we have that the weight in y is equals to what? Because if that same angle is the same as this angle, then this becomes your adjacent, then this becomes your opposite. So what is this? So this is now your adjacent, and this is your opposite. And this is the longest one that we have, your hypotenuse. So if we define this using our Soha Katoa, what is WY. So using that, remember this is the adjacent, so we must use the cosine. So it's the weight times cos of theta. Okay, while what is our W in X? Our W in X is the same as this one. So it is not, that is our sine. So it's W, because this is a W, the longest one is W, which is your weight, times what? Times sine of the angle. Okay, so if we plug in here, remember we say that to do mg, you say weight is calculated with mg times cos of theta. So if we do m is what? We say m is 20. We multiply that with, if we multiply that with g, must take what you are given, but whenever you are doing the calculation, you always use 9.81. Multiply that with a cos of 30 degrees. What answer are you getting?
Now it's 19 places. 19 places.
I got 169.9 141
169.9.
9141842.
Let's just say 9 Newton. Okay, then we go and calculate. Go on and calculate what is the components in Y. I mean in X. The weight in X, which is still mg times the sine of the angle. I'll just use the zero there. Then we have mg, we say that is 20. The m is 20 times 9.81 times sine of 30 degrees. What answer are you getting?
$98.
Okay, 98 newtons. Okay, so you will see, okay, this is the, in Y we get 169, and in X we got 169. So which means your weight, the total weight, the weight is going to be equals to the square root, which I can't put up here. Okay, so I can just write it like it's a square root of WX squared, the weight which is in Y squared, plus the weight in X squared. Okay, so it means we have to take a square root. So you must take a square root of 169.9. You square that one, square, you plus 98 square. What answer are you getting? So you have 169 plus 9, you square that, you add 98, you square that, you take a square root. What are you getting?
I'm taking a square root.
You must, this is a magnitude.
I'm put Mm. Oh, meaning, oh, first then I have to square them first.
No, when you're calculating the magnitude is most equals to the square of y. It's like you square the value in y component plus the value squared value in x component, then you take a square root of everything
Mm.
when you're doing the magnitude.
We can get attached sometimes, but what happened is for this aren't just going on. And beginning our program from now on, it's good that there'll be no more problems with you and Saga.
What answer are you getting?
I'm getting thousands.
Yeah? Did you square?
Yes, I did.
Okay. Okay, perform 169.9 squared plus 98
Without the square root first.
squared, then take a square root.
961.9 square plus 98 square, and then 934855.64. Now it's 966.
I'm getting 196.1.
100.
196.1.
Yeah, wait for the last time. 196 point.
No, the first one, is it 196 or 169?
Oh, it's 169. 69.9 square plus 98. 38. 196?
Yeah, 0.1, eh?
Yes.
Okay.
Mm.
Yeah, so it means that is your weight. So now remember we said that a normal force is equals to the weight in y. So it means the normal force there is equals to the weight that we calculated there, 169.9, while our magnitude, or yeah, our weight is equals to 196.1. So what we get here, the relationship is, we just say that the normal force is greater than, so you can see even from our values, we have a normal force which is equals to 169.9, and we have a weight which is 196.9. So a weight is greater than the normal force.
Now, okay, how did you make, well, oh, you cancel the thing.
Well, what, were you having a question?
Yes.
Just ask. Just
When you're
ask.
coming up with the y axis and then x axis.
How did you come up with the y-axis and x-axis?
Yeah, let me say, for instance, you have that object which is on
You have an
horizontal
object
stuff.
which is inclined.
Mm.
So you have a normal force acting in that direction. You have a weight which is always pointing towards the center of the earth. Then now the force which is opposing that force, this is a normal force. The force that is opposing that force is this force. The force that is acting now, you can see your weight is acting in components.
Mm.
So you have a weight which is going in y, the vertical weight, which is opposing the normal force. And you have a weight which is going in that direction.
So is still
This is
my
the weight in x direction. If I say, okay, this is my y and this is my x.
Mommy's here now, don't cry. Have you fed her? No. I also have to go home, madam. My baby is alone at home. I've been here since this morning.
Are you fine there?
okay.
Look,
Okay, this one is a
your weight, this one here is
the in between one.
acting
Yes.
in components. The one with I'm just highlighting. This one is acting in components. Is acting in y component. You can see it's kind of like this. It's not straight. You see, if this is horizontal like this, then you have an object there, then your weight is just going like this towards the center of Earth. But now, since this is inclined, your surface is inclined, then your weight, remember we say that the weight always points downwards towards the center of the Earth. Where is your Earth if this surface is like this? It's not this one.
So it's not going to be straight.
This is most your weight. Now the one which is now going in the vertical component, because now your vertical component, your x is now, I mean your y is now this one. Your y here is no more this one because this thing is acting in components. So form up your y nicely in such a way that you have y nicely and your x nicely. So you choose that this if this surface is like this, then my y is in this direction and my x is in that direction. If your surface is like this, I can say okay. If your surface is like that, then you can say okay, this is my object, my y is on this direction and my x in that direction. Or you can say in that direction. It's yours. It's yours. As long as the upward one, the one that is pointing vertically upwards, is the y-axis, and then you can choose. Should my x-axis goes on that direction, or should it goes on this direction? The positive x-axis.
I'll teach you today, and from tomorrow, you'll make milk for your sister. Let's go.
Do you get it there?
Are you sure this girl will manage everything?
Yeah.
Yes.
You got it?
Okay. Now, okay, go to the first one that you draw. This one, the one that you draw.
This one.
The first one, the one that the one that you bold.
This one.
With the weight, with yeah. Now, like this, you choose already your y-axis and then the x-axis.
Yes.
The one.
The x-axis is pointing like this direction. On this side is my x-axis. This is my x going in this direction is my positive x-axis. Because if this, it makes it easier for me not to work with negative numbers. Because if for this object, let me say if this object has to slide, this object will not slide going up, it will slide going down this side.
But this that side,
Unless there's a force, unless there is a pulling force which is being applied from this side, which is trying to lift this object going up there. So like for that example, it's like we have an object which is okay, but still all you do is, but still whether I said it is, it's like this one here, this surface from this edge up to here, this is my x-axis. But I say okay, from this point, if it is moving up on this direction, it's still on the x-axis, but this is my negative x-axis.
Oh, okay.
And this one here, I choose my positive x-axis to go in this direction.
The distance.
I'm going to show you how to feed her the milk.
You
Okay, I got
understand?
it. Yes, I got it now.
Okay, so we have seen that. So we have seen that question. So even when we calculated, we have seen that a weight is greater in magnitude than the normal force. Okay, so for example, determine the acceleration of an object mass m on the frictionless surface A. Okay, on the frictionless surface inclined. Okay, so you see that if your object is inclined, why is this one not? Okay, so if your object is inclined, I will try to use both cases then. If this,
Mm.
okay, let me say this is how your incline looks, like on that direction, and this is your object. Okay, so we say that this is the weight, which is always pointing toward the center. This is the normal force, which is always perpendicular to the surface. Then they are saying this is frictionless, so we have a normal a weight, as we say, split in two components. It's split in the x component and in y component. Okay, so let me say this is my positive y, like going up, it's my positive, and going on this direction here, this is my positive x. Okay, so then we have a force, the magnitude of, remember it looks like this, the magnitude of the weight, it's in that direction. Because you see, this is how it is. This is your weight. So this thing will not go like this. The weight in x is not like this, like pointing in that direction. It will never point here because your weight is going on this direction. In this case, the point, your weight here in the x, that splits in the x, will follow the direction of your weight. It is now on this direction. Okay, so if this object has to accelerate, since there are no other forces acting, they are saying this friction is, that surface is frictionless, there is no friction. So it means there is no other force which is opposing that force in the x direction. And this object, when it starts to slide, it will not slide going up. Do we have any force? Can this object move up?
No.
Okay, it will not move up, it will only slide following the surface like this. In which direction? In the x direction. Okay, so doing the summation of the forces in the horizontal, because now our concentration here is just the horizontal surface. The vertical one won't help us, that we don't need anything from it, because the only is asking us to do to find what the acceleration of the object will move with. Okay, so applying the Newton second law that says the summation of the forces is equals to the mass times what? Times the acceleration. And this object will only concentrate on the forces in what? In the x. So what are the forces acting in x? We only have the weight which is acting on the x, which is equals to the mass times the acceleration in the x component. What is our weight in x? Because you can see it's acting in components. So we have an angle theta, so you can say this is still the same angle, because if we draw our surface, we will it will be made up with an angle theta symbol. So this is the same angle there. So that's what we did there. If this is our W, so we have that is W times sine theta. So we have that our Wx is equals to W times sine, almost red cos, times sine theta equals to the mass times the acceleration in x component. So therefore, we know how to calculate our weight. Remember, our weight is equal to the mass times the gravitational acceleration times sine theta equals to the mass times the acceleration in x. So the mass, so therefore what are we asked to calculate? We are asked to find the acceleration. So the acceleration is equals to the mg times the sine of an angle. You divide this by the mass. You see, we took most the mass from this side. We divide on both sides by mass. So this mass, this is the same mass, cancels out, and then you're only left with g sine theta. So if we know what the values of g is, we know what the angle is, we can calculate the acceleration. You get it there?
No.
Okay, so we have that here. Our
What is our angle?
This is our
Angle.
yes. What I'm saying, if we know what the angle is, if we are given what the angle is, then we just calculate. Like in that question, the angle is not given, so we leave it in terms of the unknowns. So we always leave it if there is no value it is given, you always leave it in terms of the unknown. Is it clear?
Yes.
Okay, so we have another force which we call, what is this now? Another force that we call tension. These are the forces that are acting in the body. Okay, so these are the things that are acting on the body. So a tension is refers to the force exerted by a rope or a cable. Okay, so the force is actually like things that are attached by, if you use an object is attached together, maybe by a spring, attached by a rope, attached by a cable, then the force is equals to is the force exerted by the object, or exerted to an object either by a rope or by a cable, whatever is connected to it. And the tension is always directed along your rope or along your cable. Okay, so if you see here, you have an object. If you have an object and you attach a rope, okay, then your tension is always the same direction, like it's towards your rope. It doesn't change onto this side. If there is no rope attached on this side, there is your tension is not going on this side. It's always directed towards your rope. Okay, so and it's always pulling the object. So if let me say like in this diagram here, and then you change, if you change the rope to come on this side, then you have a tension, because it's also this one is always a pulling force. It's either pull it up or it pull it down. It will never be a pushing force. You cannot push with a rope. Okay, so The mass, when we do the calculations for finding the tensions, the mass is always negligible. So you always neglect the mass of the rope. We always say it's massless because it's the mass. It's always the mass of the rope is always small compared to the mass of the object. So always ignore the mass of the rope. Okay, and always make use of, or we always make an assumption that the rope does not stretch. Okay, so and if there's a pulley connected, like if you check in the next like the other diagrams, diagram B and C, you say it's connected towards the pulley. So if there's a pulley connected, we always say, okay, we assume again that the pulley, there is no friction on the pulley and the pulley is massless. It does not, the mass of the pulley does not affect the force on the rope. Okay, like if you look up on these two examples that you have there, so you have a mass 1 and the mass 2, they are connected together with they are connected together by a rope. Okay, so you will see that you if you look up into object 2, the tension is directed towards that side where the object is going. I mean where the rope is. So it's directed towards this direction. But at the same time, since the rope connects a mesh 2 and the mesh 1, so the mesh 1 has the tension, okay, which is in the rope directed towards the direction of your rope. The one that you see here, ignore this one. Here is the force that you are applying to pull with. Okay. And one thing that we need is if the objects are connected together, this object always moves with the same acceleration. So there is no way like one object will move greater, like with higher acceleration than the other object. They always move with the same acceleration because you are applying the same force, you are applying the same tension. Okay, so these two objects, the objects that are connected together, they move with the same acceleration. Only unless, okay, they will move with the same acceleration, but unless maybe just on the opposite directions. Like if you consider, like, did you do the experiment for the H-rod machine?
Yes.
Okay, so you have realized that as you do the like when you are doing that experiment, you have seen that as one object is pulling down, the other object is going up. So these two objects, okay, so you have an object connected like together like this, okay, and maybe there's a pulley there. So this is a mesh 1 and this is mesh 2. Okay, let me say this is, okay, let me say this is just mesh 2 and this is mesh 1. These two objects are connected together by that rope, by that string or whatsoever. Then you realize this is a tension going in that direction. Okay, and the tension of this M2 is going up on that direction. The acceleration on A2 is moving in that direction downwards, while the acceleration on A1 is moving upwards. Okay, so the acceleration of these two objects or the two masses are moving up with the same acceleration by just in the opposite direction.
So
You have a question?
No, no, I just realized it now that because I never knew if this acceleration are the same.
No, okay. Okay, so the acceleration is the same, but just in the opposite directions.
Direction.
Okay, so when we are calculating that, we keep in mind when we have connected objects. Okay, so this is just we spread the other one there up. So it's like we make use of the, if you are asked to calculate the tension, or you're asked to calculate what, make sure, as I said, when we are talking about the Newton third law, we said you have to separate the two objects. Remember that this the reaction forces are acting in two different objects. Okay, so you separate them and you write all the forces that are acting in that body. Okay, like for these ones, like for that box one, the one that we were doing first, we see that, okay, on that box we have the forces. The force that is acting in that object is only the tension, and the one which is acting in box one is, we have a tension which is on the, like on this side, and then we have a force which is on that side. Okay, let's do an example. We have this, what we were doing, a pulley is set up with 40 kilogram to the left. So we have a mass kilogram, 40 kilogram to the left, and we have a 60 kilogram to the right. This is more likely like the actual machine. Then what is the acceleration of the left side? And what is the acceleration on the right side? And what is the tension and the pulley? Okay. Oh, I'm just seeing something here. They have a new share there. Okay, so this is how we have. This is how they are saying we have something connected. So we have two masses. We have a mass here which is equals to 40 kilogram, and we have a mass 2 connected on this side, it is equals to 60 kilogram. Okay, so these two are connected by a pulley somewhere there. Then they are asking you to calculate what is the acceleration on the left side. Let me say just on the 40 kilogram, and what is the acceleration on the 60 kilogram, and what is the tension. Okay, so I said you first have to draw your what? Your free body diagram to help you to identify all the forces that are acting and in which direction. If I say this one here, it's my positive y-axis. Choosing that as my positive y-axis. Then I have here, if this object is released, the acceleration on this side will go up. Because this object, the 60 kilogram is more than a 40 kilogram. So the 60 kilogram will pull up the 40 kilogram. So the acceleration on this side will be upward, while the acceleration on this side will be downward. Okay, so we draw our free body diagram. Okay, let me just make use. If this is 1 and this is 2. Okay, so if you draw a free body diagram on body 1, then we have a force on the tension. This due to the rope. Where is this one pointing? It's pointing upward. We always say the tension always points towards the rope. Okay, and we again have what force? We have a weight force. Go to this. Okay, this is a normal force. I mean, this is an object, so you don't put up a normal force. The only forces that are acting upon this object is the tension force and the weight. Okay, so we can say our normal force in this case is a tension, because that force is directed towards um the acceleration. Now we draw again the free body diagram for what? Okay, the acceleration for this object is going upwards. Okay, then we draw for body 2. For body 2, we have a tension which is on the spring, which is downward, is directed upwards. So it's always towards the rope, and at the same time we have a force of gravity which is going down with on this thing. Okay, so we have a force of gravity on that object. The acceleration of that, as I have indicated, is downwards. Okay, so we have identified all the forces that are acting on the object, on each of that object. Okay, so if now we have to go on and make use of the what? We make use of a Newton's second law. Now, Newton's second law says the summation of the forces is equals to a mass times the acceleration. So all the forces that are acting on the object is equal to the mass times what? Times the acceleration. So we write for each object, we write it differently. We don't mix them. So for object 1, what are the forces acting in the object 1? The forces that are acting in object 1 is the tension force. It is pointing upwards. It is positive. We minus, it's pointing downwards toward the negative direction, minus the weight. This one is equals to what? Is equals to, it is mass times the acceleration. Then we go on to mass 2. On mass 2, we have the forces that are acting on that body is the tension force, which is pointing upwards, so the positive is positive, minus what? The weight of mass 2, which is equals to minus mass 2 times the acceleration. Why do we have a minus there? We have a minus there because the acceleration is towards the negative direction. Are you getting that?
Why it's a negative?
We have a minus on the negative on the its second equation because your acceleration is pointing towards the negative direction. It's going downward.
Yes, you can proceed.
Okay. So now we have two unknowns in these two equations. So we have two equations with two unknowns. So we have the acceleration and then we have the tension. So it means we need to eliminate one of them. So what should we do? Let's say we want to eliminate out the tension first, and then we can solve for the acceleration. If we eliminate out the tension, then we have that the tension, we add the two equations. So if we add the two equations, so we have this equation minus the weight 1 equals to the m1 times the acceleration, and we have this equation minus the weight 2 equals to minus m2 times the acceleration. How will we eliminate out one of them? We can do by subtraction, because this one, the acceleration is very difficult to eliminate because this is two masses. This is m2, m1, this is m2. Okay, so we subtract the two equations together. If we subtract the two equations together, this one goes. Okay, then we have that minus weight 1 minus weight 2 becomes positive. Weight 2 equals to the m1 times the acceleration minus becomes positive m2 times the acceleration. Okay, now we can solve because we know all this. The only thing that we don't know here is the acceleration. So we can go on and solve what is our
Sorry, miss. You said weight 1 minus weight 1 minus weight 2. It will give you minus.
I have a minus. Remember, we have a weight station minus the weight 1. We have a station. How I bring my pen back now? We have a station minus the weight 1 equals to the mass 1 times the acceleration, and we have a station minus the weight 2 equals to minus the mass of 2 times the acceleration. Now you want to eliminate out the station. Now you want to eliminate out the station. What did we do? We subtract the two equations. Are you getting that? In order for us to eliminate out the station, we subtract the two equations. Are you getting that?
Yes.
Should I proceed?
What I wanted is how, because now you put W minus WM plus W minus 2. How did you substitute this one now?
Okay, let me just write it down here. We have a station.
Oh, you just...
The two equations are these ones. Is station minus the W, the weight on the object 1, which is equals to the mass of 1 times the acceleration. That one is equation number 1. And we have another equation that has station minus the weight on 2, which is equals to the minus mass of 2 times the acceleration. That is our second equation. Now we have two unknowns with two equations. So the better way is so we go on and say, okay, since we have two unknowns, two equations, you can either by using the elimination method or using the substitution method. Okay, let's use the elimination method, because the substitution method is you have to make one the subject of the family and then substitute on the other one. The elimination method, you take your two equations minus W1, the weight of 1, which is equals to the mass of 1 times the acceleration, and subtract out, this is a station, minus the weight of 2 equals to the mass of 2 times the acceleration of 2. If I subtract these two equations, subtract the two equations, What are we getting? I take now the first equation minus the second equation. Why do we have? The tension cancels out, isn't it so? Are you with me?
Yes.
The tension cancels out if we subtract those two equations.
Yes.
Okay, what is remaining? Remember, we are doing subtraction. Okay, so the first equation was having minus W. So what is minus weight 1 minus weight 2? So you left, because there the minus you still carry it. It's weight 1. Now you have a minus. Because your weight 2 was also a minus there. What does a minus become? I'm asking a question.
What did you say?
Minus becomes what?
Minus.
If I have a minus.
It will be a positive.
Okay, so it's gonna be a positive. So that's why we have plus that weight 2, which is equals to the m1 times the acceleration. Then we have a minus m2 becomes positive times the acceleration. And this same equation is the one that we have over here. Now, do you understand? How did you get here?
I just don't okay.
Okay, can you just subtract the two equations on your own? Can you just take those two equations?
Yeah. Okay, did you just put them like how did you substitute the WM with 2?
No, those two, this one, which WM?
W1
this one is weight
W2.
2. This one here is weight 2.
Okay, weight 1 and weight 2. How did you substitute so that you get negative weight 1 and 2 within a place in the middle?
Okay, do you have your two equations?
Yes.
Write your two equations. Now subtract the two equations. Subtract equation 2 from equation 1. What do you have?
No, I just don't know how will I just, because this one is a 1 and then the other one is a 2.
Just subtract the two equations. You are subtracting. I have 2. I have 6 and I want to subtract out 4. You are doing exactly the same.
This one are not numbers.
Yes.
Not numbers.
Yes. Now you just write in terms of those unknowns. Subtract the two equations.
I'm not left with anything.
You should left with anything.
Unless I'll just put them the way they are.
It's not the way they are. Why do you mean the way they are? It's not the way they are.
Just maybe to take the weight 1 as it is, and then now
okay, look
minus.
at this. Look. we have two equations. We have station
Yes,
minus
that's one.
the weight one, which is equals to the m1 times the acceleration. Then we have a tension minus the weight 2, the W2, which is equals to minus the M2 times the acceleration. Do you understand those two equations?
Yes, but
Okay.
now what I cannot get is just the weight one and weight
Okay.
two. Just the way you bring up
Subtract. Now I
the
have
answer.
to. Okay. Now I have two equations. Now I am going to subtract equation 2 from equation 1. Then t minus t will just cancel out. 2 must just be a 0. Isn't it so?
Yes.
Then now I have a minus. I just brought now my sign. Let me just bring my sign minus here down there. Then I had a minus weight 1. So I'm working with a minus weight 1. Okay. I brought and then this one is now this would be a plus. Now I'm going to take a weight 1 minus weight 1. Then I'm going to subtract out minus weight 2. Do you see this? Now I have, okay, let me maybe write it.
Yes, I can.
Minus 1. Okay, and this is again a minus weight 2. Let me maybe write it different here. Then I have, let me draw this one out there. Then now I'm going to subtract these 2. So you have a minus weight 1 and you have a minus weight 2. Now you are going to subtract these 2 together. What do you do?
Okay, this one minus. Okay, maybe it's okay. It will be negative weight 1.
Okay, negative weight 1.
That's all.
No, you are taking
Because
a
I'm
negative weight 1 minus out a negative weight 2. Let me give you an example using numbers. I have a 6, a negative 6, which is now this one is representing my weight 1.
okay.
And I have a negative 4, which one this one is representing my weight 2. When I'm doing subtraction, I go most on and say minus 6 minus 4.
Yes.
So this one is the same. Now my negative 6 is my negative weight 1 minus out my negative weight 2. And then what I have is my negative weight 1 plus, because a negative becomes positive. Are you getting that now?
Okay, let's just proceed. I'm maybe going to get up because this. I'm going to do it to see how it's yeah.
Okay, so I have to write now my equations. Is t minus 1 equals to the m1a and the t minus the weight 2 equals to the m2. There's a negative here. Negative 2 m2a. Okay, then when we did a subtraction, when we subtract the two equations, we get that the t cancels out. So this one we get that it's a minus weight 1 plus a weight 2 equals to the M1A plus the M2A. Okay, so now we have our terms, so we can solve for acceleration. We know what that our W, we say we calculate our W, our weight is equal to the mass times the gravitational acceleration. So therefore, our weight 1 is minus M1 times the gravitational acceleration plus the M2 times the gravitational acceleration equals to, I can factor out the acceleration because this is what we want to find. It's the same out. Okay, then I can have is M1 plus the M2. Okay, so then which means I can find out what my acceleration is. My acceleration is equals to, I can factor out G from this side. And what is my G? I can take M2 so I can have negative on the other side. Don't get confused here. I just move M2 to this side. So it's M2 minus the M1. Divide this by, I mean this one is in bracket. Then I divide it by this one here, which is M1 plus the M2. So therefore, our acceleration, we know our values. They said our M2 is equals to a 60. Our M1 is equals to a 40. Okay, so if we substitute these values in here, okay, so if we substitute, okay, so I must just erase this. Where more of whiteboard. So if I take this, I just wanted to clear. Okay, so let me just clear this. So if I take that, remember we had that our acceleration from the last equation we have is equals to the gravitational acceleration times the M2 minus the M1, this one, divide this whole thing with the M2 plus the M1. So putting, we know all these values, we can say, okay, our G, it's 9.81. 9.81. Our M2, we have a 60. We subtract out a 40. Then we divide this with, and the M2, which is a 60, we add 40. So this is the same as a 20. Because 60 times 40 is what? Is 20 times 9.81. To divide this with the up one is a 60 plus 40, which is 100. What do you get? It's a 20 times 9 is 20.
I get
What did you get?
1.96.
Okay, so it's 1.9. I'm now typing 1.96 meter per second squared. So we found that our acceleration is equals to that. The question was what is the acceleration on the left side and on the right side? I said that if the two objects are attached together, then the two objects are moving with the same acceleration, but what? In the opposite?
Opposite this direction.
Yes, on the opposite directions. We can even also see it on our diagram here. It's 2 and this is 1. That's the same diagram we had. So we say that this is the tension going up in that direction. Since 2 is more greater than this one, then this one will move this one, while this one will move up there. So the direction of the acceleration on the left side is upward, while on this one is downward. So we have that on the left side, we have an acceleration which is 1.96 meter per second up. This one is on the left side. But what about on the right side? On the right side, we have an acceleration which is going up, downward. So on this side, the acceleration is downward, while on this side, the acceleration is. So we have that in A, the one that is asking the acceleration. So in A, we have that the acceleration is equals to 1.96 meter per second upward, while in B, we have an acceleration which is 1.96 meter per second going downward. Or you can simply indicate with a negative sign there. So the acceleration on this on the right side is negative 1.96, while the acceleration on the left side is the positive 196. The question C is asking you to find what? Is asking you to find the tension. So question C is asking you to find the tension. What is the tension in the pulley? So what we do is we make use of our original equations. So we make use of our two original equations. The two equations we had is T. We had tension minus the weight. It's a tension minus the weight in one equals to the what? Mass on that object times the acceleration, and a tension minus the weight 2 is equals to the minus mass that. So from A, we have found what our acceleration is. So we can use any of the original equation to find our tension. You can either choose to use equation 1 or equation 2. So if I use equation 1, from there we have that if making the T the subject of the formula, we know that the tension is equals to the mass 1 times the acceleration plus the what? The weight of that object. So we know what our mass is, which is a 40. We know what our acceleration is from A, which is 1.96 And we know how to calculate our weight. We say that our weight is equals to the mass
Okay.
times what?
Um,
Times the gravitational acceleration. So our weight is
sorry,
40.
miss.
Yes.
At the acceleration, are you not are you going to choose, or you're just going to take randomly? Because we have a negative and then a positive answer.
No, the acceleration is the same. It's only the direction. Remember here, you're looking for, you are looking with the magnitude.
Okay.
So even if you choose the second one, the value that you are putting up here, if you choose the one with the minus m2, you simply put up a 1.96.
All right.
The acceleration is the same, but the direction is different. Okay, so this one is 9.81. And then when you get it, you will get what your acceleration is. So and then we get this is equals to 470.8. Is that what you get?
Well, do you still have to add the gravitational one?
Yes. You simply make use of the two equations. You choose one of the equations that you want to use. You can use any of the two equations, and then in the place of the acceleration, you simply put up the weight here. You see, when you're calculating the weight is always due to the gravitational acceleration. So that one doesn't change. The weight is always due to the gravitational acceleration. It has nothing to do with the acceleration.
Okay. Why did you put this 40 here?
Which one? This one?
Yeah.
This one here.
Mm-hmm.
It's a mass. Weight is equal to mass times the gravitational acceleration. You can calculate it. You can simply calculate and put it there.
Okay.
You got it.
Like we only at this side we only have weight now, which you said is a gravitational.
This equation, you have two equations. Let me just rewrite our equations. We have two equations.
No, we must.
The tension
Yes,
minus
and then we choose the
weight one is equal to the mass 1 times its acceleration. And we have another equation which is tension minus the weight 2, which is equals to a minus mass 2 times the acceleration. So I said to solve for the this is equation 1 and this was the equation 2 that we had. So I say to solve for the tension. This is the same tension. So you choose one of the equation. So you can choose any of it out of these two equations.
Yes, and then we choose the first one.
If you take the first one, then we have make the type of the formula now. What do we have? If you make the tablet of the formula, what do you have?
We're going to have okay, 2, 1.
You simply move that weight 1 to the other side. Making T the subject of the formula.
Okay. There, got it. And then we put the
Okay, and we say how do you calculate the weight? We say to calculate the weight is equal to the mass times the gravitational acceleration.
Oh, okay. Oh.
So on place of that weight, we simply put up mass times the gravitational acceleration. Maybe let me just put it down there. It's mass 1 times the acceleration plus the weight, where we calculate with a mass times the what? Gravitational acceleration. You get it there?
Yes.
Okay. So what is our mass 1? Our mass 1 is 40. And what was our acceleration? Our acceleration is 1.96. And we add now the m1 times the gravitational acceleration, still a 40. Our mass is a 40 times a 9.81. You get 470.8 Newton.
Oh,
That's what you get.
Okay, let me confirm.
Huh?
1.96. Give me 2 seconds. 40. 9.8. Is that 4 at the end?
It's Newton. 470.8 Newton.
Point. Mine is 470.4 Newton.
Okay, let me check.
40.
40 times 1.96 plus, did you use 9.81 or did you use 9.8?
9.478.
Or you use 7 point, yeah, that's the thing. So if you have used 7.78, because me I've used 9.81.
9.78.
I mean 0.81.
But no, it's like if I use 7.8, it's going to give me 469.6.
Yeah. So it depends now which one you use. It's always important. You don't use any values, use what is given. So either in the exam or in the test, they will tell you which one to use. As long as you understand.
Okay.
Yeah. Okay, so that one helps you to check there. So this is what we had there. Like if you even check in my notes there, I even used 4.8, so it doesn't matter. Just it's very important to check which one is given. Okay, so I will end with, I think, with this one, the apparent weight. The apparent weight is just the same name as the normal force name, but this one is mostly referred to the weight that you can feel, okay, like between your body and your surrounding. Okay, like for example, if you are in the lift, okay, so it's like the way you feel when you are in the lift, when you go up and when you go down, you don't feel the same. Or do you? Did you try to do that experiment?
When what?
Like when you're in the lift, in the elevator. The way you feel when you go up and when you go down, do you feel the same? Do you feel the same?
No.
You don't feel the same. Okay, so
it's like when
now
you
with that one,
like,
sometimes you will don't feel the same. Okay, so now you will find sometimes referred to as an apparent weight, or just referred to normal weight. It's just the same. But now that one is the apparent weight we mostly make use of. So it's your weight, the way you feel, okay, like your body and your surroundings. How do you feel when these things are combined together? So it has to do mostly with your surroundings. Okay, so it's like when you are in the elevator, if the elevator is not moving, then your normal force is equal to your weight. You mostly feel the same like that. But when the elevator is moving up, let me say if the elevator goes up, then you feel more heavier than when you go down. Okay, so if you are in the elevator, this is the elevator, okay? So remember we talked about the normal weight, the perpendicular force, and this one, it's your weight. Now, if you are not moving, if you look up at the first case, you are just standing, this elevator is not moving at all. Then what do you do? If you are not moving, if you sum up, then there is no acceleration upon that object, isn't it so?
Mm-hmm.
Are you gone?
No, I'm around.
When you are at rest, we say that when you are at rest, you don't have any acceleration. Then we say that the acceleration is equal to 0. So then if you use the Newton's second law, then we say if you add up your forces, then this is equals to 0. So if the elevator is not moving, then you have that your normal force is equals to the weight. This is what you feel when you are going, when you are just standing on the elevator and nothing, the elevator is not moving at all. You feel the same. Okay, let me say, okay, if you are going up, if the elevator starts to move up now, then what do you feel? This one is normal, this one in this case is out. Now let's say you are in motion going up. Okay, so now you start to move up. Move up now. So the elevator starts to move up. Then what we have? We said that, okay, if we say this is up, which is a positive, ne? Moving up, we have a positive y-axis. Then summing up the forces there, we have that a normal force minus your weight is going to be equal to the mass times what? Times the acceleration. Okay, then what will be a normal force when you are in the elevator? When your elevator starts to move up, then we have that the normal force is equal to mass times the acceleration plus what? Plus your weight. So you will see that, you can see from this one, you can see that your normal force is, you will feel up, when you, as you go up, you feel more heavier than your weight. So this is what you will feel. Let's try to use some numbers. The acceleration is always very, the acceleration of the elevator will be smaller compared to the acceleration of due to gravitational concentration. Let me say we have an acceleration of the elevator which is moving up with 2 meters per second. Let's say this is the acceleration of your elevator. Just put up numbers here. If you have a mass of 60 kilograms, okay, then 60 times 2 is what? So you have a 60 times the acceleration of the elevator times the weight. Remember we said your weight is what you have, which is your mass times the gravitational acceleration, because this, your weight is always due to the gravitational acceleration. So we have a weight of a 60 times a 9.78 or an 8 point whatever. Let's just use 7.8, 9.78.
Okay.
So we have 60 times 2 plus a 60 times 9.78. Why do we have? we have that this is equals to 706.8. Is this what you get?
Yes.
Okay, so it means when you go up, you see what is your weight? If it is your weight, what is your weight? Your weight is 60 plus it's 60 times 9.78. So your weight, which is 60 times 9.78, you have 586.8 Newton. So you will see that on your weight, you added up something. So you will feel more heavier when you go up than when you will feel a more of like 200 and something. Like 7 now, this your normal weight will be 706.8 as the elevator moves up.
Did you multiply or add?
Multiply the weight, or which one?
Yes, the weight.
The weight is not mass times mass times the gravitational acceleration.
Oh yeah.
Okay, now look at the case when the elevator starts to move down. Is what happens to your normal force. I'm new to the normal force. Does it decrease, increase, or stays the same? Do you feel the same when you go down? Okay, using again the Newton's second law, we said this is our up, it's our positive y-axis. So then using the Newton's second law, summing up the forces, the normal force is pointing upward, is positive, minus the weight is equals to a minus mass times the acceleration. Why is minus? The acceleration is decreasing, is going in the negative direction. Okay, so then we have a normal force is equals to a minus, now make the normal force the subject of the formula, that plus your weight. Okay, let's do the same. You have a weight of a 60 kilogram and you are accelerating downwards with a 2 meter per second squared. Okay, then you take a minus. What is the mass? It's a 60 times the acceleration of 2. Then you add your weight, which is the mass times the gravitational acceleration, which is a 60. We say times that with a 60 times 9.78. Okay, 9.78. What do we get? We have minus 60 times 2 plus a 60 times 9.78. Why do you get? You get 400. Is that what you get?
466.8.
66.8. Yes. So you will see that. Remember, like from our calculation there, we had a weight of 500 and what was it? 580.
586.
86. Yeah. So you will see that when you go down, as your elevator go down, then you feel a bit lighter compared to your weight. Okay, so this is the same example that we have. So just by plugging in those things there, you will see the value. That's what we were doing. It's exactly the same what we were doing. Okay, so we'll start with friction force next time. Okay, go study. Did you do
Next week?
Yeah, I think next week. I will put up a notice on
All
the.
right. Next week.
Excuse me.
Okay, it's fine. I wanted to ask if it's Monday or Tuesday.
Oh, because it's like now we have to be online most of the time. But I always have to put up a notice on the Moodle, ne?
All right.
Like join for a class on what.
All right.
Yeah, we can even do it. I will check if tomorrow. Yeah, but I'll put up a notice if even if it's tomorrow. So maybe on Monday we can even start maybe with circular motions. Yeah, but we will see.
All right, miss.
Yes. Unless you have questions. If you don't have questions, go enjoy your lunch.
All right. Thank you. Likewise.
All right.
Oh, what's up?
And the meeting.
My phone also.